Okay,
I can see.
great. Well, thank you, Laura. Thank you, Mark, for the introduction, and thank you for the opportunity to present to you today. So, as the title of my talk suggests, I'll be talking about the industrial sector and more specifically about decarbonization of the industrial sector. So for those of you who have interest in climate change and the role of materials or new process technologies in addressing climate change, I hope you can find the presentation interesting. For those of you who may not know much about the role of industry and the technologies we have and don't have when it comes to addressing climate change, I hope you can potentially learn something new. But I'll try to keep the presentation brief. I'll try to be high level to give you the chance to ask a lot of questions. So with that, let's go ahead and get started. Let me make sure I can advance. Okay. So as requested, I will be presenting in two major segments. In the first segment, I will try to set the scene. So where are global greenhouse gas emissions headed? How important is the industrial sector when it comes to current emissions, but also to addressing climate change? And then what are the technology levers that we have as a society? The ones we have already developed, the ones that we could develop in a sufficiently rapid time frame in order to start decarbonizing the global energy sector. So a lot of the results that I'll present in this first segment come from the time I was able to spend at the International Energy Agency. So I spent 2 years there between 2015 and 2017, where I was part of a modeling team, and our job was to try to identify and communicate pathways for deep decarbonization. And so I'll show you some public results arising from that work. But now that I'm back at Northwestern and no longer affiliated with the IEA, any interpretations are clearly my own interpretations and not those of the IEA. And then in the second half, after we have the chance for some Q&A, I'll talk a bit more about my research. I'm part of a small but growing, and I'll posit too small of a research community, but it's a growing one, using engineering modeling, systems analysis techniques to try to identify opportunities for emerging technologies to rapidly address sustainability problems. So I'll talk a little bit about the state of the art, and I'll give you some examples from my own research. How are we applying some of these techniques in what I'm calling bridging the laboratory to systems analysis gap? So working with the innovators, developing new technologies, how can analysts make sense of those technologies, use modeling, use simulation to provide the hard numbers that policymakers and investors need and manufacturers need to accelerate adoption of those technologies. And I'll focus on two particular cases: additive manufacturing and carbon capture materials. So with that, I'll kick into part one. Where does the world stand when it comes to greenhouse gas emissions? So what you're seeing here is about a 20-year, not quite 20-year timeline of global energy-related CO2 emissions. So these are not 100% of all the CO2 emissions coming from the planet, from the Earth, or from the anthroposphere. These are the emissions associated with the energy sector, which is defined as any sector of the economy that consumes energy. So this is both supply and demand. It represents about 2/3 of all global greenhouse gas emissions. And as you can see here, it's been on the rise. So in the period 2015-2016, the world experienced what we hoped would be the beginning of a plateau and a downward trajectory. In 2017, however, the world ticked up again with respect to overall emissions. And the arrow that you see there for 2018 was an earlier prediction by the IEA, which has since turned from a prediction into an actual recorded data point. So unfortunately, in 2018, global energy-related CO2 emissions rose by about not quite 2% due to rising energy demand, reaching a historic high of around 33 gigatons of CO2. So the message is the world is moving in the wrong direction. And urgent action is needed to put us on a pathway that will help limit global warming to 2 degrees or even less. So what you see here are some results from the IEA's Energy Technology Perspectives Report 2017. These are results coming from the team that I was part of when I was at the IEA. And what you see here is a widening gulf over time between where the world is likely headed. This is the so-called reference technology scenario, the RTS, that's the red line, and where the world needs to go with respect to keeping long-term global warming to 2 degrees Celsius or less. So the results I showed on the previous slide indicate that we are still headed down that red pathway. So what does that red pathway imply? Well, just for context, these are the results of a really comprehensive global energy systems model that the IEA maintains, and there are other institutions that have built and run such models throughout the world. But what they try to do is represent in great detail the technology makeup of the energy system, inclusive of supply and then all of the demand sectors, and show the net emissions effects of different energy systems configurations. So that red line basically is the IEA's central outlook as of 2017 for where the energy system is headed based on current and announced policies. So what does that red line contain? It contains all of the pledges coming out of the Paris Accord, the historic agreement, which nearly every country in the world has signed on to limit global warming. So there were a lot of really great aggressive pledges made coming out of the Paris Accord, but they're not near or even less. So at best, it looks like if the world follows this storyline, emissions will plateau around mid-century. And where the world needs to go, the carbon budget is the green line. To limit global warming to 2 degrees or less is the green line. So it's really the job of energy systems modelers and analysts to identify how can we bridge that gap? How can we go from that red trajectory down to the green trajectory? So what you see here is a so-called wedge diagram showing the contribution of energy efficiency, renewable energy technologies, fuel switching, nuclear energy, and what we call CCS, that's carbon capture and sequestration, for providing guidance to primarily policymakers, but also manufacturing companies, the energy industry, for the technologies that need to be adopted in order to change course. And this is a somewhat simplistic representation. It's very high level, but underlying each of those wedges are hundreds of different technologies in all major world regions that map out a transition pathway for the 2DS. And as you can see here, the world still has a lot of opportunity to adopt energy efficient technologies to reduce energy demand. And there's still huge opportunity for the world to adopt more renewable energy technologies. That's a big part of the challenge, but it's really difficult to get to a 2-degree trajectory without increasing reliance on nuclear energy and adopting carbon capture and sequestration. The ETP 2017 report, which is what I'll focus on moving forward, laid out an even more aggressive scenario, which was called the Beyond 2-degree scenario. And the goal was to see if the world could reach net zero emissions by around mid-century, consistent with the goals of the Paris Accord. So the Paris Accord specifically said the aspirational goal is to limit warming to well below 2 degrees, not just 2 degrees, but well below 2 degrees. And that B2DS trajectory you see there, reaching net zero by around 2060, is consistent with around a 1.75 degree warming carbon budget, a 50% chance of that. And you can see to get from the 2 degrees to the B2DS, it requires an even stronger push in some key technology areas, all the while potentially adding 3 billion people to the planet over this time frame and ensuring that everyone on the planet has a reasonable standard of living, equal energy access, access to basic energy services. So it's a really tremendous challenge. So global emissions are on the rise, and they're continuing to do so without major technology interventions. So what is the role of the global industrial sector? So what I'll show you now are the direct emissions in the RTS, the IEA's central outlook in ETP 2017. So as you might imagine, the electric power sector is the single largest source of direct greenhouse gas emissions. By direct, it's on-site fuel combustion occurring within the sector itself. The industry sector is the second largest and projected to remain that way through mid-century, followed by transport, buildings, and agriculture. So the message here is that industry, even though it's not something we often think about, when we think about addressing global warming, many of us tend to think about solar panels and smart homes and Teslas and wind turbines. In fact, the industrial sector is really nearly the single most important sector to decarbonize if we are going to reach net zero emissions by mid-century, because it also uses a lot of electricity. Transportation is also very important. They're all important, but most of us don't think about the industrial sector when in fact we can't get to net zero emissions without massive industrial sector decarbonization. And it's going to take all technology options that are on the table. So what this graph shows is a simpler representation of the wedges I showed earlier. To reach the 2-degree targets that stay within that carbon budget, as I mentioned earlier, it's going to take a really strong push in energy efficiency, renewables adoption, and CCS. But when we think about reaching an even lower temperature target, the beyond 2 degrees scenario, the push really comes in greater energy efficiency. So bringing all buildings to a really, aggressive energy efficiency standard, maximizing the energy efficiency transport vehicles on the road. And we really can't get there without a big push in carbon capture and sequestration, which is what you see in the lowest bar graph there. We need all of those technology levers. We need really strong pushes in all categories. And this is particularly true in the industrial sector. So what I'm showing now is the wedge diagram for the industrial sector itself. The top scenario is the RTS, the central outlook, where industry is headed, given current and announced policies. The key thing to take away there is the trend looks somewhat similar to that of the overall energy sector, but that a plateau could be reached by mid-century is really an enormous achievement in and of itself, because as I'll show you in a few slides, there are a lot of factors driving industrial energy use up, and the sector has made a lot of improvements and is continuing to make a lot of improvements, reducing its overall carbon emissions. But to get to a beyond 2-degree vision, a lot more decarbonization is needed. And when it comes to industry, there are some different levers that are available. One is material efficiency. I'll talk about that. Clearly, we still have energy efficiency and adoption of best practice technologies. But if you focus on the lowest wedge, the dark green wedge, that's really where we need CCS in order to reduce industrial CO2 emissions. And you'll notice that the B2DS does not get to net zero for the industrial sector. And the reason is it's very difficult to decarbonize certain end uses within the industrial sector that may continue to rely on fossil fuels, and it's not possible to capture 100% of the CO2. What does that mean? It means to get to net zero, those emissions have to be met through so-called negative emissions technologies or through greater carbon sequestration outside the energy sector, somewhere else in the global system. And that's another important takeaway, and it just underscores how difficult it is to decarbonize the industrial sector. Part of the reason is the world is demanding more and more materials to fuel development, for greater population growth, greater economic output. And what you see here on this graph is the 5 so-called energy-intensive industries. That's the global cement, steel, petrochemicals, aluminum, and pulp and paper sectors. In each one of these categories, in the central outlook, the world will require more materials produced each and every year, making it even harder for the industrial sector to reduce its emissions, because it presents a dual challenge. We have to reduce the amount of emissions per unit produced and also reduce the overall amount of emissions while at the same time producing more and more materials. So it really is a really strong challenge for the industrial sector. When it comes to looking at the big picture, an important piece of decarbonization, not just for industry, but for the residential sector, for the transport sector, and every sector, frankly, is the decarbonization of electric power generation. So what you see in this graph is on the left-hand side, the fuel mix for the global power sector in roughly the present day, 2014, the base year of the analysis. It's, as you know, probably we still are quite reliant on fossil fuels. So the majority of global power is still currently met with coal, with natural gas, a bit with oil. And that picture needs to change drastically moving out to mid-century if we are to reach net zero emissions. So as you follow the graph from left to right, As we get out to mid-century, renewable energy forms like wind, solar PV, hydro energy, greater use of biomass, even more nuclear deployments make up the vast majority of the electric power mix by mid-century. And this orange line, which you're seeing here, is the CO2 intensity per kilowatt generated. That metric has to go negative around 2050 in order to provide that negative emissions sink to make up for positive emissions that occur elsewhere in the system, like in the industrial sector. And you might be asking yourself, well, how is that possible? How can we have a negative CO2 emissions intensity, that we have negative CO2 for every kilowatt hour we generate? And the answer is we rely on what is known as BECCS. So BECCS is an acronym that stands for bioenergy with carbon capture and sequestration. And the concept is illustrated in this diagram here. So if you train your eyes on the center of the diagram, which you see is represented by, biomass, trees, energy crops, and so forth. As we all learned back in, middle school biology, plants need CO2 to grow. So plants are a natural CO2 sink. They pull CO2 from the atmosphere. And you probably already know that through other beyond the classroom lectures. That carbon is then it's part of the biomass itself. And we have, two major ways of using it presently. We can, if you follow the diagram to the right, we can burn that biomass and generate steam and run it through a steam cycle. And if that CO2 were to be emitted back to the atmosphere, as long as we were planting more biomass, an equivalent amount of biomass to suck up that CO2, we'd have what is known as a carbon neutral use of biomass. The CO2 emissions would be sucked up by subsequent generations of biomass. The idea with BECCS is, rather than let that CO2 go off into the atmosphere, if you look at the smokestack, we capture that CO2, we put it underground, and therefore we're enacting a continuous carbon sink. So the electric power sector becomes a CO2 emissions sink, making up for positive emissions elsewhere in the energy system. And if you follow the graph to the right, the same phenomena can occur for producing biofuels. A fraction of the biomass is used for energy. When we produce biofuels for transport use, we have to capture that as well. So that's how we have negative emissions intensity in the global power sector. And the reason that's important is, if we zoom out for a minute and look at the importance of negative emissions technologies like BECCS, we can't get to a low carbon future really in any major scenario that's been analyzed by any major institution without the use of so-called negative emission technologies. So what you're seeing here in this graph is a really intuitive graph, hopefully, from a Nature Climate Change publication by researchers at YASA, who have a large integrated energy system and an integrated assessment model that also runs decarbonization scenarios. So what you're seeing here is a lot of different scenario runs. The blue dots are runs that were able to limit global warming to a budget consistent with a 1.5 Celsius temperature rise. The orange are scenarios that had a likely 2-degree scenario rise. And if you read to the right, I gave you the definition. And then the light pinkish dots are the scenarios that led to a medium probability 2-degree temperature rise. And if you look at the x-axis, that refers to emissions that the world emits between now and 2050. The y-axis is the emissions that the world emits between now and 2100. So if you follow that linear line, running diagonally across the middle of the plot, that represents the condition where we essentially don't emit more by 2100 than we emit by 2050. And if you fall below that line, which is what's required for every blue 1.5 degree scenario, it means we have to emit less over time. So put another way, we need negative emissions technologies. And if you look at just that scattering of data points, you can quickly realize that in order to meet the world's low carbon ambitions, we're really going to need negative emissions technologies in nearly every scenario that we could posit. So they're critically important. And what does that mean in the context of this presentation? Well, what I'm showing now are the present day, 2014, base year, bioenergy utilization globally. Presently, the world, most of the biomass we use goes into the building sector, and this is modern biomass energy usage for things like wooden pellets for heating or cooking and so forth. Under the central outlook, the world will continue to use more and more biomass just based on current policies and trends and pledges. But increasingly, that biomass will have to be used for biofuels and also the power sector. And that black dot shows the percent that is captured and becomes a negative emissions sink, which is more or less nil. Looking out to the low carbon scenarios, 2 degrees scenario, beyond 2 degrees scenario, the world will have to make use nearly of every joule of available sustainable biomass on the planet. And a large fraction of it will have to go to the power sector and the fuel transformation sector to provide the BECCS negative emission sink. You can see from the black dot that about 30% of all that biomass utilization has to be associated with BECCS in order to achieve net zero. And what that means is there's less left over for the industrial sector. And this could have implications for the types and quantities of biomass available for, let's say, biochemicals or biopolymers or other uses of biomass that we can envision as being sustainable if the world is to achieve net zero, given the current technologies we have and the technologies that we can envision coming down the pike. We may have to divert bioenergy into negative emissions technologies and away from maybe some other potential end uses in order to achieve net zero. So the structure of biomass utilization and the available types and quantities of biomass for other sectors could really depend on what the world does when it comes to negative emissions technologies. And that has implications. So now I'd like to talk just briefly about CCS in general. What is the status? So for the power sector and for the industrial sector, CCS is a really critical technology. The good news is that the world has already embarked down this pathway. There are 18 large-scale commercial operations already in place. There are 5 under construction, and there are around 20 in various stages of development. And this is a nice plot showing when the projects were either commissioned or will be commissioned in time. So there's already quite a few that are in place today. The size of the bubble is the amount of carbon that's being captured on an annual basis. And the y-axis shows the different sectors which are deploying CCS. And historically, it's mostly been in the oil and gas industry. We do have a few plants that are in the industrial sector and more of which will come in the future. And the colors show that most of the projects are being used for what's known as enhanced oil recovery. So enabling existing oil extraction to extract more oil. There are still very few that are what are known as dedicated geological storage. That's permanent carbon sequestration somewhere. So that's the good news, is the world has been moving on CCS, and it is happening. And this is a plot of the large scale projects in a more simplistic way, showing the already commissioned and planned projects out to around 2025. So this is the good news. But now I want you to pay attention to the scale on the left-hand side of the graph. So we're sequestering, tens of metric tons globally. But in order to stay on track, just for the 2 degrees scenario, in 2025, that's the gray bar you see on the far right, notice that the scale has now changed. So put another way, when we zoom back and we look at where the world needs to be in 2025 with respect to the amount of CO2 captured, if you contrast that against where the current and planned projects are going, you can see that the world is about an order of magnitude off track when it comes to the amount of CCS that needs to be deployed. So we need to accelerate massively the adoption of CCS in order to stay on track, even for a 2 degree warming carbon budget. And that's important for the second half of the talk, because CCS, as I mentioned, plays a critical role in the industrial sector. And I'll talk a little bit about how we're doing some work, and others are, analyzing CCS technologies. And it really is critical for the industrial sector, because this is a somewhat maybe confusing graph at first. So bear with me. What you're seeing are three different scenarios. The orange colors are the RTS, the green colors are the 2DS, and the bluish colors are the beyond 2 degrees scenario for three different heavy industries: chemicals, cement, and crude steel, which are represented by different shapes. And so just how much CCS do we need in the industrial sector to reach a beyond 2 degree vision? Well, if you look at the year 2060 and you look at the dark blue cluster of dots for these three heavy industries, around 70 to 80% of all the direct emissions coming from these three sectors will have to be captured and sequestered, meaning nearly every cement, chemicals, and crude steel plant will have to be equipped with CCS to keep global warming to low levels. So I'm going to talk a little bit more about CCS, but I'm also going to focus on materials efficiency. So just as some quick context setting comments before I wrap up and take questions, materials efficiency is a growing area of attention for decarbonization and for meeting other sustainability goals. And really the goal is to meet the needs of society with far less materials dependency. So improve recycling, reusing building components, lightweighting vehicles. Are there technologies, are there processes, are there strategies for just producing less carbon intensive materials in the first place so that we reduce demand and therefore make the decarbonization challenge a bit easier for the other technologies we need to get there? So I'm going to focus on those two aspects moving forward. But at this point, I'd like to break and see if anyone has questions on the big picture part of the presentation, which I just presented. Into a really important field of research, which I'm simplifying with this label of emerging technology analysis, but one that my research lab has been involved in since day one, and which I will advocate for in my slides as being really important for helping figure out how do we accelerate these technology transitions. And I've chosen a couple of examples that hopefully will resonate with everyone on the call. And so the first one is additive manufacturing. And I don't know if you've been exposed to additive manufacturing directly. Maybe you've used a 3D printer at home, or maybe your university has some and you've seen them used. I am going to focus on metals manufacturing because that's where most of my research has been. Even though I recognize that we can print polymer parts, as you see here, and that's the thing that most of us are familiar with. But if we think about additive manufacturing or 3D printing as a class of technologies, it's very kind of mature when it comes to the hype curve, right? You'll hear a lot about it. So 3D printers are going to change the way we manufacture everything. Articles in The Economist. Who needs the Paris Climate Accord when you have 3D printing in Forbes? So there are those who think that making parts or products anywhere, anytime, in demand, anywhere in the world is just the climate mitigation wedge we need. It's going to help us get to a low emissions future. And there are even some projections that say, it's really going to replace traditional machining and traditional manufacturing processes quite rapidly. And so if you're a policymaker or a technology investor, or even a manufacturing plant who could benefit potentially from additive manufacturing, it's difficult to know what's hype and what's reality. And technologies like additive manufacturing haven't been included in a lot of those global climate and energy system scenarios, one of which I just showed in the first half of the presentation, because there isn't sufficient data, sufficient maturity to the technology, and sufficient credible information for analysts to represent those technologies in their model and to suss out whether or not there is a real opportunity here for climate change or any other sustainability issue. So the key message is that there's often a lot of hype around emerging technologies, and that is because there are a lot of potential benefits which are starting to be proved at the lab scale, at the pilot scale. So when it comes to additive manufacturing, or AM for short, there could be quite a few potential benefits, some of which I'm showing you here in this bullet list on the side. So the picture is, a diagram of kind of the layer by layer manufacturing process. So rather than making metal parts by, casting ingots and machining them, or using forging or subtractive manufacturing techniques. We make pretty much the part we want directly in layer by layer fashion. And this could lead to a manufacturing system where we no longer use tools, dies, or forms. The parts are near final shape, so they're very materials efficient. We can make them quickly, so there's reduced delivery time. There's a lot less inventory potentially, and we should be able to save lots of time and money by moving to an additive manufacturing paradigm. Could these benefits be true? Yes, I will show you in certain cases, but are they true writ large for any application of additive manufacturing? Well, we're going to dive into that question in this presentation. So where are the benefits coming from? So there are leading industries that are adopting the technology. The aircraft industry is one. Why is that? Well, as you see here in this diagram that just popped up, there are aircraft companies who are already adopting additive manufactured parts for things like hinges, brackets, other fairly simple parts. The compelling business case for them already is that if they want to make, let's say this is a bracket, this is the way the part looks in the present day on the right. They need to start with about 10 kilograms roughly of raw material, let's say in this example, to get to a 1 kilogram part. So it's a highly subtractive process. They're getting a block or a shape of titanium alloy, nickel alloy, whatever. And there's something that's known as the buy to fly ratio, which captures the mass of material they start with divided by the mass of material that makes its way into the final part. And that buy to fly ratio can be quite high for certain types of parts and certain types of alloys that may not be formable in certain ways and so forth. And so the reason this industry is interested in additive is because they can make that part on the left-hand side, which you'll notice a couple of things. First, from the text, they start with a lot less raw material because there's a lot less waste in the manufacturing process. There still is waste, but there's a lot less of it. So perhaps they can start with a little bit less than a kilogram of raw material. And the finished part is also a lot lower in weight because of the design flexibility that comes along with additive manufacturing. So the aircraft industry, a big profitability issue for them is fuel use. Flying all that freight and people around, all those people around, uses a lot of fuel. So the lighter they can make their aircraft, the more profitable their operations have become. And this is the driving factor for adoption of the brackets on the left versus the brackets on the right. That's a strong business case for them. So there are many potential benefits of additive manufacturing, but it is a technology that's evolving quite quickly, and it does still face a lot of technological and economic barriers in a lot of applications. So there are some limitations to the technology. They include, residual stresses when you heat, cool, in layer by layer fashion, especially in some processes like SLM, you build up residual stress. And as you can see from the sort of finite element analysis diagram down at the right, those can lead to potential liability points for parts that are, subject to loading or fatigue life requirements. Surface roughness can still be unacceptable. There still could be some machining required. The dimensional accuracy of the process is improving. It's still quite slow compared to some high throughput processes like stamping or forging or other conventional manufacturing processes. Which alloys are available? They're still a limited class, and as we'll talk about in a few slides, is it cost effective yet? So how does a policymaker who wants to look at a roadmap for decarbonizing their country make sense of additive manufacturing when there's a lot of hype, a lot of potential benefit, but a lot of important barriers to consider, and there's very limited analysis? No hard numbers on how to make sense of that technology. Could this be a technology that would offset the need for CCS or nuclear energy? They don't really know unless we can include them in the scenario models, and we can't do so without a new focus on a new area of modeling, which I'll go over next. So the other important point is a lot of the benefits and barrier could be highly application specific. So the aircraft companies are adopting those lightweight brackets because they make sense in that application. And worst case, if they were to break, the plane wouldn't fall from the sky. But could they put them on the blades of the turbine running within the engine? That's a completely different risk proposition, and the benefits there might look entirely different. So there are some challenges within the analysis community for analyzing technologies like additive manufacturing and many others. And some of them I'll list here. So these are technologies that are evolving rapidly with limited empirical data. It's not that, the labs, the companies, the adopters of additive manufacturing aren't publishing data, but they're often not the type of data in the right form with the right breadth for an analyst to model that technology in a credible way, like we can model like an electric vehicle or a solar panel. There are multiple stakeholders in the value proposition for a technology like additive manufacturing. So who can help accelerate a technology like this? Well, it could be the plant operators who would adopt this technology and replace a conventional technology. They might care about, what is the implication for my inventory, for my materials costs, for my ability, for my lead time, and so forth. A policymaker might care about the cost of the technology and its ability to reduce emissions. An investor might care about what's the opportunity for this technology in different markets and so forth. So another difficulty is analyzing these technologies in a way that's relevant to the multiple stakeholders who can accelerate its adoption. And doing so in a way that's meaningful for specific applications. So the value propositions for the aircraft industry might have certain, a certain look about it, but the value proposition for, let's say, the injection molding industry might look entirely different. When it comes to a lot of these technologies, there also may be a lot of upstream effects to consider. If we think about additive manufacturing, if it uses a lot less nickel, titanium, steel, aluminum, and so forth, there'll be potential energy and emission savings upstream through less mining, less freight, leaner logistics, but potentially even downstream. So if we're producing better parts through additive manufacturing, what does that mean for the end use sectors that adopt these parts? Would they be more efficient? Would they reduce their emissions and so forth? All of these challenges are quite difficult for analysts like me to overcome without a lot of research. And part of that research is moving into developing partnerships between the innovators of technologies. So perhaps a lot of you on the call are working in experimental or maybe even demonstration type projects where you're trying to innovate and bring to market a new material, a new technology. It's important for that community to work much more closely with the analysis community, the community that I'm a part of, so that we can start generating the analytical insights, the hard numbers that these stakeholders need much earlier in the process. So I'm going to give you a quick example about how we're trying to tackle this challenge for the specific case of additive manufacturing. And what you're seeing here is a high-level diagram of the types of modeling frameworks that need to be developed. So I mentioned that these models that are assessing, in this case, what's the sustainability of additive manufacturing in different applications, what are its cost implications. These models have to appeal, as I said, to multiple stakeholders, and they have to encompass the entire life cycle system. So the first aspect to these models is that we need to take a life cycle approach. You've already had, I believe, a course on life cycle assessment, so perhaps you'll recognize kind of the system boundaries of a diagram like this. But in order to assess the true carbon footprint of additive manufacturing, we have to go all the way back to the mining of the materials, their transformation into the basic material inputs that go into the process, how those materials are used in the conventional system on the left and the additive system on the right. When they go off into the economy, do they have implications there? And so we have to capture a number of flows, resource flows, energy flows, emissions flows, to capture the sustainability implications. We also have to capture, because this is an emerging technology, the engineering functionality of the technology itself. So these models we don't want to spit out a result that says, we take that case study of a lightweight bracket, which shaved 80% weight off, and we apply it to every part on an aircraft, because different parts have different functionality, and the state of additive is not sufficient to meet all of that functionality. So these have to be very engineering-oriented models that capture the end use in terms of the functionality that's required for a part. Otherwise, what might happen is the model will select additive for a class of parts for which it has no business being deployed because it can't meet the surface roughness requirements or the reliability requirements. We have to also include a strong economic dimension. Adopters care about the cost, policymakers care about the cost. And if you're a plant operator, you're going to care about things like ongoing O&M, inventory, lead time. And finally, when it comes to advising policymakers and investors, we have to capture the level of technology readiness and simulate, its present readiness, but in the future, if certain targets could be met, what new savings opportunities could be tapped through technological maturity. And all of this has to happen in a dynamic fashion, considering that the whole system will change over time and its benefits, its costs, all of its parameters may vary on a spatial basis. So, the use of electricity is important in additive manufacturing. If that's occurring in China, it'll have a certain carbon footprint. If it's occurring in, the US with the lower, with a slightly greener carbon intensive power mix, the benefits may change. So it involves integrating a lot of tools: life cycle assessment, energy systems modeling, traditional production economics and engineering process modeling, but coupling the models with, let's say, detailed representation of materials properties is another important aspect. Why is all this needed? Well, hopefully this will become clear in a quick case study. So, one of my first PhD students here at Northwestern spent 4 years building this comprehensive model, pulling together these different modeling techniques and data sets that are used in these different fields, and developed a nice comprehensive integrated model, which we then wanted to apply to a specific case study. So I'll show you how can these types of models provide meaningful insights on an emerging technology in a real world application. So we decided to focus on the aircraft industry and utilize some data that we were able to get, thankfully, from the Boeing Corporation on the types of components, the different component systems within typical aircrafts. And we were able to piece together prototypical manufacturing supply chains, geographical locations, and so forth, so that we could populate the model with a case study looking at the US commercial aircraft fleet. What would be the benefit of deploying additive manufacturing over the next few decades for decarbonization of the aircraft fleet right here in the US? And to do this, a hallmark of this type of analysis is, again, we want to avoid broad brush analysis, taking a single case study or a few case studies that give us some idea of the savings in one application and applying it in broad brush fashion across an entire end use or entire sector. We have to avoid that. Otherwise, we're giving the wrong advice to potential stakeholders. So these analyses involve going through the entire, market application, in this case, aircraft, looking through the different component systems, whether each of those components within each system is structural, functional, is it a low-hanging fruit thing that could be replaced today, or is it highly functional that we won't be able to replace until we're able to produce parts that won't fail in high-stress environments, and track all of that, market applicability at the level of the specific alloy, the specific component system, to know just how much mass could be replaced in an aircraft over time. And then in the second table, we also have to include technology readiness. So there are certain component classes, for example, the first row on the table, auxiliary components and body systems or furnishing systems. We can start replacing some of those parts either today or in the very near future based on the maturity of the technology and its engineering functionality. But there are probably applications like propulsion systems, as you see in the table there, where we won't be able to deploy additive manufacturing turbine blades until we have a high degree of reliability. We've overcome residual stress challenges for that application, surface roughnesses, challenges, and so forth. And that might not happen for 20 years. So how do we simulate those sorts of deployment strategies in a model like this? So granular instead of broad brush analysis provides the analysts and its stakeholders with much greater insights into where are the market opportunities today and in the future for a technology like additive manufacturing. So what you're seeing in this graph is an example of 5 prototypical applications of additive in aircraft. So if you look at the images across the top and the labels across the bottom, brackets, seat buckles, and so forth, each part has 2 plots. On the left is the energy footprint of producing the part through conventional manufacturing processes. And the right-hand column has the same footprint, but through additive manufacturing. And by just scanning the diagram, right away, you can get the sense that there are some types of parts for which additive really could save a lot of energy and could really be a nice decarbonization technology. But there are other parts, for example, like the seat buckle or the bionic bracket, where conventional manufacturing already does a pretty good job. Perhaps you know that seat buckle is made of steel sheets that is then stamped and bent, and we don't get a lot of savings out of additive manufacturing. So we can use models like this that represent the end use level in sufficient detail that we understand the engineering functionality, the materials limitations, and we can start identifying, okay, well, where does additive manufacturing beat conventional processes today? So these findings are true even more broadly than the aircraft example, but within the aircraft example, these are smaller production quantities due to throughput limitations, parts that are highly complex, which could be made more efficiently and better through additive manufacturing processes, parts that have a lot of material scrap already, low mass because the throughput of these machines is still somewhat slow. So the less mass you have to lay down, the faster the part can be produced. And most importantly, significant redesign potential. So if you can take an existing part and suddenly now with additive, you've opened up design flexibility that you didn't have before. Those are really the sweet spots for additive, but they're not generalizable. It's really important to make sure you're understanding and modeling the end use in sufficient detail so that you capture the right applications. So that's the first benefit to these sorts of models. The second benefit is that we can begin, when we understand the areas of the market, the applications where AM could be deployed today and in the future, subject to sufficient technological process, we can begin to use these models to analyze scenarios that look at, okay, the present day for a technology like additive manufacturing is to gradually adopt it, and maybe in the future we start building new planes with additive manufactured parts. So we have a slow adoption scenario here on the left. What does the scenario entail? Well, these are projections from the US Department of Energy's annual energy outlook on the number and demand for aircraft in the US domestic fleet. So as you can probably imagine, Americans are traveling more and more. So we need more and more aircraft over time. If we just follow a business as usual pathway, additive will be adopted. It's already being adopted, but that adoption pace will be somewhat slow. It'll be somewhat conservative. Are there other adoption strategies, deployment strategies that could be pursued, assuming that we can develop the technology so that we minimize risk and only deploy it when it's ready? So we can posit that there are other scenarios, like scenario C, rapid adoption scenario, where the technology progresses really quickly, we hit all of our development milestones, and the aircraft industry starts replacing parts in existing aircraft with additive, and then every new plane maximizes its adoption of additive manufacturing parts. So these are two, A and C are two sort of, ends of the scenario spectrum. What we want to do when we run these models is look at, well, if we follow one path versus another, what does it mean for the amount of potential greenhouse gas emission savings? So by running these scenarios, we can help identify policies to remove potential market barriers. So the red scenario at the bottom, that's the business as usual scenario. The blue scenario at the top, that's the rapid adoption scenario. There's a lot of uncertainty in any of these scenarios, and it's quite large when we get to the rapid adoption scenario, but there still is a big difference between the red scenario and the blue scenario, meaning that if we can overcome some of the basic technology barriers, deploy the technology faster, we're likely to reap large savings. And the faster we do that, the sooner we can start potentially reaping the decarbonization benefits of additive manufacturing. And models like this, by running these different scenarios, looking at different what ifs, we can show, agencies like the Department of Energy, which by the way funded this research, I should have mentioned that earlier, technology investors, okay, if we could overcome, surface finish issues sooner, residual stress issues sooner, these are opportunities to invest in more basic research. What would be the payoff if we could reach those milestones sooner? Well, the payoff would be we could start moving from the red scenario to the blue scenario. Now we could put a number on the potential carbon saving benefits for the planet, for the nation, by using these sorts of models as a powerful what if engine. Policymakers can also invest in pilot and demonstration projects so that potential adopters of additive don't have to take the risk immediately. They can look to a successful project and learn from it and so forth. This is another tried and true policy mechanism. Scenario analyses like these can help inform those decisions. And what if we can bring costs down? All of these questions are things that we can simulate in a scenario exercise to put a quantitative, hard, credible number, even if it's a range, on the potential benefits of those actions. But to wrap up on this example, can additive manufacturing, save resources, save energy? We found that, yeah, there is a compelling benefit to saving resources from additive manufacturing. So, in the rapid adoption scenario, the US used a lot less titanium, aluminum, nickel than it normally would through the adoption of additive manufacturing. So there is, a lot of truth to the hype about additive saving resources. But what we found is the much larger saving opportunity comes from designing better parts that we simply couldn't manufacture using conventional processes. So what this graph shows is the total energy savings of additive manufacturing adoption. The smaller bar at the bottom, labeled 88, those are the energy savings associated with avoiding material scrap. Not negligible, but compare that to the large section of the bar, the 1276. That refers to the energy savings of lighter weight aircraft in the economy. So the real potential benefit to additive could be not that it saves so much energy and resources at the manufacturing plant, but that the parts that we produce go off into the economy and they save a lot of energy and emissions in their end use applications. And so policymakers and adopters should widen their perspective to think about the big picture so that perhaps early adopters of additive manufacturing won't save so much energy and resources, but what it does is it benefits their customers. That's an important hook that comes really into focus when we utilize modeling techniques like this. I'm going to skip this cost example because I want to leave time for questions. I'll just note that these models can also capture the costs, the lead time implications, the inventory implications, a lot of the metrics that technology adopters really care about. So that also takes modeling in a much different way. But I want to quickly focus on another example before I wrap up and turn it over to questions. So that first case focused on a technology system that is already in place. So there are companies, there are machine tools that are already cranking out additive manufactured parts. And so what if we were to focus our attention in the modeling on technologies that aren't yet market ready, that are at an earlier TRL level, that are in the process of being innovated at the lab scale? I want to show you how the sorts of models that I just demonstrated can also be useful in these contexts. And in this particular case, I'm going to focus on a class of materials known as MOFs, metal organic frameworks. Perhaps some of you have heard of these materials. They're gaining a lot of attention. There's a lot of research going on because they could do a lot of interesting things, because they have a very high surface area to volume ratio, and they could present a really attractive material for low pressure storage of hydrogen for fuel cell vehicles. In this case, the research team at Berkeley, prior to my arrival at Northwestern, funded by ARPA-E, was embarking upon a high throughput discovery process for metal organic frameworks for carbon capture, and in this case for carbon capture from coal-fired power plants. And they were looking at a lot of different combinations of metal ions, organic linkers, different temperatures, different reactant ratios, and so forth, trying to discover MOFs that would be stable and cost-effective and up for the task of capturing carbon at a large scale in coal-fired power plants when deployed. So research teams like this, they have a pretty good idea of where they'd like to go, but how do they manage the complexity of many, many different parameters that could be optimized to produce MOFs that will ultimately be competitive for carbon capture? That's where having a partnership between the lab and modelers or analysts like me can really provide some early insights that can add value to the research process. So in this project, it was quite exciting. We were able to work in parallel with the high throughput discovery process and work very closely with the chemical engineers who were doing the lab work to try to understand and envision what would this technology, what would success look like for this technology when deployed, and what would be the physical and economic systems that would be in place to help this technology succeed. So what we did was we developed what's known as a prospective systems model. So in this sort of research, we are trying to develop a model that is like a virtual test bed for the technology in the future. And it describes the overall system into which this MOF would be placed, and it captures all of the important physical and economic parameters in the system that would make or break the success of the technology. And as you can see here in this simple cartoon, these sorts of modeling frameworks have to include the whole life cycle. So at the very center, we have the power plants that would adopt the CO2. We have systems within the model that are known processes. So how do we model a future system that doesn't yet exist? Well, parts of that system already exist and will continue to exist. So we already have great data. We know how to model, for example, coal mining and transportation, CO2 compression and injection and transport. We know how to model, for example, the basic materials manufacturing and production processes for the ligands, the metals, the solvents going into MOF production. So parts of the system are already known, and we can do a reasonable job at modeling them. There are another important way to set up the modeling question is there a benchmark technology that we can choose, which is known, which exists, to which we can compare the emerging technology to get some sense of, will it be competitive against prevailing technologies? So in this particular project, we chose amine-based carbon capture technologies, which are already in place in different industries for a long time in different parts of the world. So this is another known system, and we understand how it works. We understand its cost structure. We can then utilize it to look at the deltas between the benchmark process and the new process. But this blue area I just circled here is really the heart of the lab analysis partnership that I'll describe. It's where we had to work with the lab innovators to try to come up with a vision for how would a physical MOF carbon capture system look when deployed at a power plant. What would be the basic parameters that would govern, for example, the number of stacks required or the time it would take to suck up a certain amount of carbon and then discharge the carbon? How much steel might be required to put that system in place? Where would it go in an existing power plant? Would it go after a scrubber, before a scrubber? This is a highly prospective exercise, but if we can capture some realistic system configurations in these models, we can then use the overall model in a more responsible way, meaning we're not trying to predict with perfection, this technology will save X megatons of CO2 in year Y. We can't really use these models for those types of analyses, but what we can use them for is to explore systems conditions that would govern the success of the technology, and then ideally feed that back into the R&D process so that the people developing the technology now have greater intelligence on, out of those maybe 30 or 40 or 50 key experimental parameters or final material property parameters that they're working on in the lab, are there some that are much more important to get right? Can we set targets for those so that they have, if they were to hit these targets and optimize certain parameters, would it maximize the probability that the technology would be competitive compared to the benchmark technology? So what you're seeing here is a sensitivity analysis diagram. This is one way we can use such models. And what we've done is the left-hand vertical orange bar has the prevailing carbon capture cost of the benchmark technology. The amine-based CCS system comes in at about $50 a ton CO2, and we parameterized all of the systems aspects for the benchmark technology and its costs that help us get an estimate of its current cost structure. We can then compare that to the possible cost structure of the MOF based on the cost of this material, the efficiency of that process, and so forth. And what you get from it is this hopefully, this intelligence that tells the innovator, out of the many things you can consider, it really is important to focus on, the mass to solvent ratio. Anything you can do to extend, even by a little bit, the lifespan of that moth is going to bring down your capital costs and so forth. So hopefully this gives some clarity and helps the research team home in on some of the key design parameters that would help close the gap between the MOF CCS system and the prevailing system in the future, so that when the technology ultimately makes its way to market, it's already homed in on the factors that would help make it more successful. So this is another way we can use models in a partnership with the lab process to help provide them with early insights that they otherwise wouldn't have. So I'm going to wrap up now to leave time for questions. So just some quick parting thoughts. Hopefully you understand the importance of industrial sector decarbonization, and you understand now that it's going to be very difficult to decarbonize with existing technologies unless we can rapidly deploy CCS. So we need a lot of innovation there. And if that doesn't happen, we need to get going on other innovation areas. One of them could be materials efficiency through greater adoption of additive, but additive, MOFs, and a whole host of other emerging industrial technologies and materials fall under this broad class of technologies that are simply just not well represented in the big picture sustainability scenarios due to lack of data. And we need to overcome those data gaps. And to fill those data gaps and address those knowledge gaps, we have in the analyst community some priority research areas that include much greater linkages between the analysis community and the technology development communities. Can we start working together much earlier in the process, share data, give insights to each other so that the models get better at representing these technologies to provide quantitative numbers much earlier, and hopefully those numbers can be fed back into the innovation process to give innovators greater intelligence into how to bring their technologies to market quicker with the right properties so that they can be taken up by multiple stakeholders. So that's one aspect. The second aspect is the types of models I showed you today. There are other research groups developing them, but it's still a bit of a wild west. We don't have really a codification of techniques and best practices for prospective modeling approaches like this. And it's a challenge to my own research community to come up with those so that policymakers, investors, other stakeholders can trust these prospective analyses more and be comfortable with the uncertainties that come along for the ride. And then lastly, one of my personal missions in my career is to help contribute to training the next generation of engineering analysts who can build and run these types of models. Because frankly, our existing degrees, training systems don't train engineers well to come equipped with the types of tools they need to build and run these models or to know what sort of data goes into them. It really takes a unique breed of engineer, someone who understands the technologies and processes at a fundamental level, but also can work with life cycle assessment techniques, economic modeling techniques, big picture energy systems models. I think it's a big opportunity that we have as educators to introduce more classes, to give students more training opportunities to become the type of analysts that can help build bridges between the lab and analysts in the future, so that the people who can help accelerate adoption of technologies have the right information when they need it to do so. All right, so with that, I'll conclude part 2. It went a little long, I'm sorry, but I think we still have some time for questions.